All right, so this is the last lesson in this trigonometry unit in which we're focusing on triangles, which is kind of maybe sounds strange in trigonometry, but after this, the focus will move to rotations. But this lesson here, which maybe it looks a bit messy just by taking a quick glance at what you see on the screen, is pretty straightforward. It's, again, like the sine law, it's another application of trigonometry for non-right triangles. But unlike the sine law, you don't have to think about this ambiguous case. So it's actually, like I said, it's quite straightforward, and this won't take very long. So again, the same sort of conventions with the sine law, that uppercase letters represent angles, and lowercase letters represent sides opposite from those same angles. And much like the sine law is always true for any triangle, this cosine law, or the law of cosines, is always true. And we see here is this, and it's if you kind of look at it, it looks similar to the Pythagorean Theorem, and it's not a coincidence. In terms of proving this, which I'm not going to bother doing, but in terms of proving this, it does relate back to the Pythagorean Theorem, or can relate back. But this is always true, where, again, A represents some side, and B and C are the other two sides. And the uppercase letter A is the angle opposite to the side that we're kind of trying to find over here. And again, it's not as messy as it looks. And so with that said, let's just look at this right here. I want to find the measure of side C. Now, I don't want to get too hung up if I look at the law of cosines here with the, that there has to be an A here, has to be a B here, has to be a C here. What really matters is that we have all three sides of any triangle, A, B, and C. Those are three sides. And again, sides B and C repeat over here. Whereas this represents the angle that is opposite to the side essentially we're trying to find. This is kind of set up to tell us, if we could find side A, well, we could find A squared really easily if we just square root A. If we find A really easily if we square root A squared. So in its essence, this is kind of set up to find side A if we want. And if we want to find side A, we need to know the measures of the other two sides, as well as the measure of the angle opposite from the side we're trying to find. That's essentially what this represents. And so looking at the question here, I want to find side C. So I could set this up by saying C squared equals my other two sides squared. And so A squared plus B squared minus 2 times. And notice whatever comes next are the same two sides we had here. So in my case now, it's going to be A times B again, times the cosine of the angle opposite from this side we're trying to find. So in this case, it's the angle of C. In fact, I'm going to make this C squared more obviously lowercase right here. And so what I have here is just the exact same thing as I gave you at the start, just the variables kind of arranged in a way that's helpful for the particular triangle I have here. So in this case, side C is this side right here. That's what we're trying to figure out. Side A is 16, because angle A is right there. Side B is 5, because angle B is right there. And angle C is 61 degrees. So notice we have everything we need in order to find C squared, and therefore C quite quickly. So in this case, I can now say C squared equals, instead of A squared, I can say 16 squared plus 5 squared minus 2 times 16 times 5 times the cosine of 61 degrees. And really, at this point, I can just type everything into my right, everything on the right. There's no variables left there. I can just type that into a calculator. And so if I type 16 squared plus 5 squared minus 2, blah, 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 I should get about 203.4. Keep in mind, that's not C, that's C squared. And so to find C, I need to square root it. And so C will equal approximately the square root of 203.4. Now you may recall, thinking back to the quadratics unit, that when we go from here to here, if you think of it as a square rooting both sides, there's two possible solutions here, positive or minus. In this case, I don't need to think about that because C represents a distance, and distances are always positive. So I don't need to think about that here because we can't really have a negative distance. So it's not wrong to think about it as long as in the end we realize we shouldn't have a negative distance. And so the measure of side C is approximately 14.3. And I don't think I had units here yet, so I can just say 14.3 units. All right, so like I said, it's actually quite quick to use, and even though the this equation here, a squared equals b squared plus c squared minus 2bc cos a, is not as kind of elegant as the sine law. It's actually quite easy to use, as long as we just realize, again, this represents the side we're trying to find, most likely. These are the other two sides, which repeat, those values repeat twice. And this angle here should be the angle opposite to the angle we're trying to find. All right, so let's look at this one. Again, I don't need lots of examples. I want to find angle C again. So angle C represents this angle right here. We know side C. All right, I also know I don't know angle A, but I know side A, and I know side B, but I don't know angle B. So let me just, while I'm trying to find angle C, I'm going to start by writing down the same equation I did before, which is set up to find side C. So c squared equals a squared plus b squared minus 2bc times the cosine of c. So that's what we're trying to find. We're trying to find that. And I know everything else. I know side C. I know side B. I know side A. So it must be possible to solve for this. And one thing I could do right now, I don't really recommend it, but one thing I could do is substitute C right away with 7.4, substitute A with 11.6, substitute B with 15.2, and then clean that up and kind of step-by-step solve for C, or the cosine of C. However, what I recommend first is I'd rather, if I'm going to isolate stuff and move things around, I'd rather not deal with all these numbers like 7.4 squared and 11.6 squared. I'd rather just deal with A, B, and C. So I'm going to rearrange my equation right now before I substitute values in. And it's quite easy to do. For example, if I just subtract A squared and B squared from both sides, I get C squared minus A squared minus B squared on one side, and minus 2 cos C on the other. Oh, sorry. It helps if I write that down correctly. Minus 2bc cos C. And if I now just divide both sides by minus 2bc, I've isolated not C, I've isolated the cosine of C. So I could get c squared minus a squared minus b squared over minus 2bc. And all that must be the same as the cosine of C. And that's fine. That's it. There's other ways I could have rearranged this. For example, if I want, and if you look on this side, there are a lot of negatives there. I could multiply the top and bottom by -1, which would just come up with an equivalent expression with a lot less negatives, but I don't really care. I'm not afraid of negatives. And so in this case, I'm going to substitute all my A, B's, and C's next. And so I should get 7.4 squared minus 11.6 squared minus 15.2 squared all over minus 2 times 11.6 times 15.2. Oh, shoot. I apologize if you saw me make this mistake earlier. I'll say this is a test. I tested. It was a test to see if you caught my mistake. If I look right here, there's a mistake. That should be an A, not 2. It should be 2BA, not 2BC. And so let me just change that to an A. There we go. Again, as I said before, the two sides we use here are always the same two sides we have here. And so that means easy for me to fix. There should be an A right there, which means I should be dividing both sides by minus 2BA, or AB, whatever. And so, again, I have the right values written down here. I just had the wrong letters up there. And I guess I could re-record this whole lesson, but I'm too close to the end to do that. So hope you don't mind my laziness here. All right, so keep in mind there, though, aside from my little mistake, which has now been fixed, everything I see here is not C. This is the cosine of C. And so go to my calculator, type in 7.4 squared minus blah, blah, blah. Maybe do it in a few steps. Be careful. Like, there's a lot of stuff going on here. You should get the cosine of C equaling about 0.881. 0.881 being all of this right here. So keep in mind, though, again, I don't want the cosine of c, I want c. So as we've seen before, if I want to figure out just side c, or sorry, angle c, I want to use the inverse of cosine at 0.881. And I should get about 28.2 degrees. There's my answer. And so sometimes students, and it's not a bad idea, they memorize two forms of the cosine law. One is the sort of form that I kind of started with right here, and another is the form after you've kind of isolated for cos c. In the end, though, as long as you just know the first one, you can always get to the second. All right, so before I go on, keep in mind I had a triangle. There was no right angles. In fact, I didn't know any of the angles, but I knew all of the sides. And so using the cosine law, I could figure out the missing angle. In fact, I could find out any missing angle. And so in general, if in general you know two angles and a side, I would always first think about the sine law. It is still, I think, simpler to explain, simpler to use the cosine law. If you know two sides and an angle in between them, so if you know a side and the angle that goes between them, the cosine law will always work. And if you ever have a triangle where you know all three sides and you need to find an angle, the cosine law will always work. In general, if you're not sure, I would always try the sine law first. It is, I said, a bit more pleasant, I think. And if you realize you don't have enough information, then you use the cosine law. All right, and here's our last problem. So this triangle here, like I said, it looks like it's a right triangle or has a right angle. Like if you look at this, it looks like that is 90 degrees. But actually, is it? Just because it looks like it's 90 degrees doesn't mean it is. First of all, is this drawn to scale? Or even if it is that 90 or is it 89 or is it 88 or is it 91? Like, I really can't tell. So I said it looks like it's 90 degrees, but I don't know yet if that really is 90. So how can I prove if this really is a right triangle? And like it says, try to think of more than one way. Well, one way I could prove this is kind of like what I just did in the last question. I could use the cosine law because I do have a triangle and I know three of the sides. And if I can use the cosine law, if I know three sides of any triangle, if I know all the sides of any triangle, I can always use the cosine law to find any missing angle I want. So that's one way I'm going to approach this. And so to do that, I'll just call this angle here I'm trying to find A, which means this is lowercase a. I'll call this B. This is lowercase b, and this is c. I'll call this lowercase c. But I'm going to use the cosine law to find angle A. If I get 90 degrees, yeah, it's a right triangle. If I don't, no, it's not. And so again, if I want to use the cosine law, I could start off with just the basic form here. A squared equals b squared plus c squared minus 2bc times the cosine of A. If I'm trying to find the cosine of A, though, I can just isolate that right away. Say cosine of A equals a squared minus b squared minus c squared, all divided by minus 2bc. And so now substituting the values we have here into this. And again, I'll do my usual highlighting thing here. There's side A, side B, side C. Notice in this case, sides B and C, doesn't matter which order you put them. They're both being subtracted from the numerator. They're both being multiplied together in the denominator. Doesn't matter. Calculate this. You get exactly 0. And so keep in mind, 0 is not A. 0 is the cosine of A. And so if I want to find A, I want to use the inverse cos. So I want to say A will equal the inverse cosine of 0. And if you type that in, you get exactly 90 degrees. And the next lessons we'll understand why, like kind of what that means, the cosine. The cosine of, the inverse cosine of 0 equals 90 maybe sounds kind of strange, but that's what some of the next lessons are about. Either way, who cares? Done. 90 degrees. That is a 90-degree angle. I now know for sure this is a right triangle. However, I said try to come up with this in more than one way. Another way that I think is actually significantly easier is remembering the Pythagorean theorem. And remember the Pythagorean theorem, a squared plus b squared equals c squared. In that case, a, b, and c represent sides of a right triangle, where c, if I write this down, a squared plus b squared equals c squared, I got to be careful. The Pythagorean theorem, this was the hypotenuse. And so I can't get too hung up on the a, b, and c I have my triangle, because again, in my triangle I've drawn, the hypotenuse is right there, which I've called a. So again, we never should get too hung up in the exact variables. With the Pythagorean theorem, what we need to get hung up on is, again, that c squared there, that's the hypotenuse. And so if this really is a right triangle, then 4.5 squared plus 6 squared should equal 7.5 squared. So 4.5 squared plus 6 squared should equal 7.5 squared. If it does, it's a right triangle. If it doesn't, it's not a right triangle. And if you go to your calculator, you'll quickly see, yeah, this is correct. 4.5 squared plus 6 squared does equal the same thing as 7.5 squared. They both equal 56.25. Which means, yeah, this is a right triangle, because the Pythagorean theorem is only correct. The sum of the squares of the two shorter sides in a right triangle only equal the square of the hypotenuse, or the longest side, in a triangle if it is a right triangle. And so the fact this works means this must be a right triangle. So if I look at these two, yeah, the one on the right, the one I just did, I think is easier to understand, but they're all correct. And keep in mind the cosine law can be applied to any triangle. And that's it.